Okay. So, these tasks we talked about and their relation to each other. So, we spoke about quite a few executive functions, switching, or you may call it shifting as well, inhibition, monitoring, planning, and so forth. And the question now, which has come up, is whether these are separate, distinguishable functions, each of them, so representing different cognitive processes in a way like short-term memory and long-term memory, for which we know they are localized in different brain areas, and they can be affected differently by lesions, and consequently different neuroanatomical localization. Or do they basically reflect the same underlying construct? So the same cognitive process and the same localization. Or is it something in between, a bit of both, basically, so that they are partly related to each other. Okay, so there was one researcher, Akira Miyake, I hope I speak that name correctly, who tackled this question in the year 2000 and published a paper about the unity and diversity of executive functions. Okay, and this paper was really kind of long awaited by the community, and so far has been cited by more than 3,300 papers. So it's a really popular paper, it's very well received. Okay, so what did they do? They in total investigated 14 tasks and tested 137 participants. And every participant performed all 14 different tasks. And it took more than 3 hours of testing. However, they split it, I think, in 2 sessions, so that it was bearable for participants. And they had so many participants and so many tasks and everything to run something which is called a confirmatory factor analysis. Are you familiar with factor analysis? Yes, no, kind of. Okay, so the general idea, very plainly speaking, is that you can set up a way, a model how your variables or concepts you see that in the graphical image are linked to each other, and then you calculate kind of a set of correlations of your different measures among each other, and you check whether this is true or not. This is a way of confirmatory factor analysis. There's exploratory factor analysis, and this is often used, for instance, if you want to develop a new questionnaire or something. You present 200 items, and then you run a factor analysis to see whether certain items measure the same thing, basically. And in this factor analysis speak, one would say whether these items load on one factor. So they correlate on each other. So they asked the question whether 3 proposed executive functions, and they chose shifting, updating, and inhibition as the core executive functions, whether they are distinguishable or whether they tap the same underlying construct. And again, in this nomenclature, these things they want to assess, they call that a latent variable. And in this context, the latent variable is basically a theoretical construct, like inhibition. It's a theory that we think there is something like a mental process like inhibition. And when we want to see whether there is really such a thing, we need some explicit task, like the go-no-go task, which measures that. So we say we have an idea of a theory, in this example, latent variable, and then we think, okay, how can we measure that? By which means? Okay, so how did they go ahead with measuring shifting or switching between tasks or mental sets? They chose 3 tasks for that. One is the plus-minus task switch by Jersel, which we talked about before. Second one is the number-letter task switching by Rogers and Monsell. And I note these authors here, but they often based their task on that and modified it somewhat. But this is the basic idea. And a third task, which we didn't speak about so far, and that's a local global task. And this has been developed by Naven, and so it's called a Naven figure. And you see you have a large letter A made up by small letters H. And so participants are required from trial to trial to switch between reporting the local letter or the global letter. So on one trial you may respond with an A, and on other trials you may be required to respond with an H on that figure. And then you can make up different large figures from smaller letters. Like that. Okay, so updating as the second big function and monitoring of working memory representations. They used first a task which is called keep track task, and personally I think these tasks are all quite challenging. And what this task looks like, you get a couple of categories told in advance. Let's say in this example just two categories, fruits and cars. And then you get words presented, one after the other. For instance, apple, Ford, bulb, Ferrari, chair, banana, and so forth. And at some point, you don't know when, you're asked, okay, what was the last fruit which has been mentioned? What has the last car which has been mentioned? So to start with apple. When you now are asked for fruit, you would say apple. Then there's Ford, then there's bulb. When you're asked now for fruits, you would still say apple. If you're asked for cars, you would say Ford. Goes on, Ferrari. If you're asked for fruits, you would still say apple. If you're asked for cars, you would now say Ferrari. And then banana, chair, and so forth. So what you have to do basically is constantly update the last word which has been mentioned in each category. You have to keep the categories in mind, and when Ferrari comes up, okay, you have to update the last word of the car category. Then a tone monitoring task. So you have 8 high-pitched tones, 8 medium-pitched tones, and 8 low-pitched tones, and they are presented randomly in a block. And your task is to respond to every fourth occurrence of a particular tone category. So in a way, you have to count the occurrences of all 3 categories, and once the fourth high pitch came, you press a button, that's the first medium pitch. So you have like 3 counted running in your head on each. And now this was high pitch, and this was the third occurrence, not pressing. So quite demanding task as well. And finally, a letter memory task. You get a sequence of letters, one after the other, and after each letter you have to speak out the last 4 letters. So when we start from the left and build up the sequence, you would say T, TH, THG, THGB, HGBS. When the K is presented, you have to say GBSK, then you see the R, you see BSKR. And of course you only see the last letter, so you have to keep everything else in your mind. So it's very strong, again, on updating and monitoring. So, and they all involve not only that you have to store something in memory, but as well that the temporal information is very important about what was the last item, every fourth occurrence, so you have to count here, and here you have to bring that in order. And by this additional component, it becomes something taxing executive functions. And we have inhibition of prepotent responses. Here they used the Stroop task, then the so-called anti-saccade task, and the variant they used looks like this. You have to fixate across the screen, then you get a black square, which you should ignore because briefly afterwards, on the opposite side, the target will appear. This is an open box with a little arrow in there. This arrow can show into one of 4 directions, and your task is to indicate as fast as possible in which direction. The task is made difficult because that is masked very quickly. So basically, when you go with the cue and look here, you follow this irrelevant cue, you won't have enough time to look here to identify where the arrow points. So, and because you have such a high time pressure, you are very inclined to look to the first point where something is blinking up. So it's quite a tricky task to keep your attention focused, to not look there, but look the other way. And a stop signal task. So where they get different words and they have to decide is it an animal or non-animal, but they are not allowed to respond when a tone is played. And they assess the performance of all these 9 tasks. So 3 tasks for each category. What they did in addition is that they used complex executive tasks which are frequently used to assess frontal lobe functions in patients. Because they wanted to not only to see how do the other tasks relate to each other and how do they form these 3 latent variables, but how well these tasks are related as well to the underlying concept. So they used the Wisconsin card sorting test, we know that one. Tower of Hanoi, we know that as well. Operation spanning we have heard. Random number generation. We haven't had that yet, however, it's a very straightforward task. You're just asked to create a random sequence of numbers between 1 and 9. And you're often cued. In this example, every 800 milliseconds you have to produce a new number. It may sound pretty easy, but it's not that easy because you tend to fall into standard sequences saying 2, 3, 4, but it should be random. So it's a bit challenging. And they used a dual task, and here they combined maze tracking. So people had to find with a pen a way out of a maze, like you find in children's magazines or something, and a word generation task at the same time. And word generation means you get a letter, like S, and then please name as many words as you can within 20 seconds, starting with the letter S. And please avoid very common function words, I think proper nouns or something like that. So it's made, after 20 seconds, you get the next letter, and you are asked to produce as many words as possible, starting with that letter. These tasks are first done individually as single tasks, and you measure performance for that separately, and then you do it together. And you then can see, okay, in the dual task, how's the percentage of performance compared to the individual performance. So dual task, you become slower, so maybe that you only produce 80% of words as compared to dual task. Okay, so, and the theoretical model they proposed looks like that. They say they have the latent variable or the executive functional concept of shifting, and this is described by the plus-minus task switching task, the letter task switching, and the global switch task, updating by the 3 working memory tasks here, and inhibition by anti-saccade stop signals, the task we just talked about. And confirmatory factor analysis works in a way that you specify that model, and then you see how well do the data fit that model or not. In addition, they tested one factorial model, so all of these are one function evenly described by everything else, or several 2 factorial models. So these are one function and separate from this and all the combinations you have. And then they try to fit the data to that. And, oh yeah, sorry. we come later to the results of that, and then in addition, they describe this more complex model where they say, okay, these complex executive tasks, like Wisconsin card sorting test, how do they relate to these latent variables? And if they are really reflecting executive functioning capabilities, they should be strongly related to one or more of these latent variables. Okay, so these are the results. We will go through them. So you will have basically the same model, the same diagram as before, but now with a lot of numbers here. And the numbers mean different things, basically. These numbers refer to the error terms. And this is sort of say, or describes how much of the variation in the observed data cannot be described by this model. And this is quite a bit. So data vary between 0.8 and 0.92. And if you square that, you have the percentage of unexplained variance. So it's between 66 and 88%, which is not explained. So the other way around. When you do the task, you know you have every person performs slightly different. So you have variance in the data. And how well person do the task can be explained by 12 to 34% by having such a model explaining the performance. So this is all significant, but you see there is still quite a bit of room for explanations. These lines show the factor loadings, and this is basically the beta weights from linear regression, or when you want to say like the slope in a linear regression. Usually you would say the steeper the slope, one is maximum, the closer the two are linked to each other. And you see it's somewhere between 0.33 to 0.63 as the highest. So these are all significant and quite alright factor loadings here for that. And finally, these lines reflect correlation coefficients. So how strongly are these latent variables are related to each other? And you see that it's like average correlation, so they are moderately correlated with each other, around 0.42 to 0.63. So these are like the numerical results. I don't want to go into too much detail here, but just to show you they calculated a lot of other models as well. This is a chi-square test, and the smaller the number, the better, basically. And for these two values, it's the smaller the better as well, and here it's the larger the better. And you can see that the full model with 3 factors just has the best fit to the data. And when you compare the models against each other, this one is always significantly better than the others in describing your data. So it actually is the best model. It really seems to be that 3 proposed functions of updating, shifting, and inhibition are 3 separate variables, because when you don't treat them separately, you can't really very well describe the data you observe. How do they contribute to complex executive tasks? So we are now looking at this part of the diagram, to the arrows from shifting, updating, inhibition to complex executive tasks. So let's first go to the Wisconsin card sorting test. And the dependent variable they took are the perseveration errors. So how many errors made people with sticking to the old rule and not changing to the new rule? And here you see that the best model is if you only model one path from the shifting concept. And how is that to read? These are the same criteria, chi-square value as we have seen before. And they just try different variants. What happens if you have one path from shifting, or no path at all, or all 3 paths? and they compare them to each other, whether one is significantly better than the other. And when they have a couple of models which explain the data to the same accuracy, so they don't differ significantly from each other, they take the most parsimonious model. So you may have a model with all three paths. This explains the data pretty good. Slightly better than this one, not significant. But it's much more efficient to only use that model to say, okay, there's only one path from shifting to explain the performance in the Wisconsin card sorting test than having to assume to other factors as well. And here are the coefficients for the three concepts, and you see the other two, updating and inhibition, contribute only very little, shifting contributes most. This is again a bit like the factor loading is like slopes in a regression. And so they decided for that model that this best describes it. So what does it mean? It means that when you want to explain performance in the Wisconsin card sorting test based on all the data which have been collected, the best, most efficient way to do is to take the shifting performance and the variable, the latent variable shifting, as a predictor of Wisconsin card sorting test. Or if you want to turn it around, you could say the Wisconsin card sorting test with the stuff tested in this study is mostly relying on your capabilities to shift between vector sets or tasks, which is kind of not very surprising, given that Wisconsin card sorting test, the crucial thing is the ability to shift between things. However, it means that your Wisconsin card sorting performance is related to the number letter task switching, to the other task switching paradigm, and this global local shift. So these two paradigms test the same underlying cognitive processes. Tower of Hanoi. This is a variant of the Tower of London task. It's more complicated by having a start solution, or how the disks are arranged at the start and how they should be arranged at the end. So it can be different, not just put them on a different pole, but it may be a different arrangement. So it's more complex to think about, okay, how do I get to this end state of arranging disks? And the dependent variable is how many moves did participants need to find a solution. And I think it was, to give you an idea of the complexity, I think 15 moves were required if you are as good as it. So the perfect solution would have been 15 moves, not less. And when they did that, they found that the best model is just one path from inhibition. So that the Tower of Hanoi or Tower of London is best described by inhibition. And their explanation of that is that if you do that task, you often have to move the disks in a counterintuitive way. So if you have to get one pile of disks onto the next peg, then you would think, okay, I just put it on the next peg. But you have to put the small disk somewhere else first for the longer term planning. And that's why people usually think this is a planning task, because I have to do that. What they show is that inhibition may be required to prevent these obvious solutions of just put it next, but inhibit that, go with the plan. However, they didn't find any relation to updating and switching. So they argue that either they didn't have a very good measure of planning in their set of tasks, which may be the case actually, and so they actually question a bit whether Tower of Hanoi is a good planning task, but probably it's more that they didn't have planning included as a latent variable, because the basic task they chose, there's not a real planning task involved. Random number generation, it's the randomness of the produced sequence they investigated. And here they found two paths which are important, one from inhibition and one from updating. And well, that's for two different aspects of this randomness. And inhibition is important in this task, most likely to suppress stereotype sequences. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, something like that. And updating is probably important because you have to keep a trace of your recent responses, and then you probably compare that to some measure of or concept of randomness. So you say, okay, my last 5 responses, did I use every number from 1 to 9? Did I have number 5 used 3 times in the last couple of tries, so I have to use it less often? So this is about updating of memory components. The operation span, so this solving math equations, remembering letters. Yeah, not surprising, again, very strongly correlated or was explained by the updating latent variable. So, yeah, it's just, you have to constantly update your memory contents, and you have to be aware of the sequential order of the items. So the operation span is very closely related to the basic tasks they used, like this tone monitoring task. And finally, the dual task, that was explained by nothing. So the best model was the no-path model, and they don't have a really good interpretation for that. They just say, well, dual task performance may require other executive functions, which are not included here. And they are cautious in a way that they say, well, null findings are generally hard to interpret. You may remember from your statistics, if you do not find a significant result, so if you can't reject the null hypothesis, then usually you don't know anything. Because there's no evidence for the fact that the null hypothesis is true, actually. It just doesn't tell you anything.
Sorry, which one was the dual task?
It was a maze tracking and word generation. So to summarize that, we can say that these 3 executive functions, they can be distinguished from each other. So different component tasks correlated with different of these latent variables in a different pattern, and they are only moderately correlated among each other. So here probably can say we have a bit more diversity than unity. We have both of that, but there seem to be different sub-functions in executive functions. The complex executive frontal lobe tasks, they are basically related, all related to one or more of the basic executive functions. So in a way, this confirms that they are appropriate tasks to assess executive functions, for instance, in frontal lobe patients, with the exception of dual task performance. Okay, do you have any questions regarding that bit? Okay, then as the last topic, I would like to talk about dual task performance, and when time permits, and I think it should be, we'll go a bit more in depth here, and yeah, see. So, dual task performance. We know that from everyday life that people often do multiple things at the same time, which sometimes is often described to women of everyday life situation, taking care of household, cooking, children, and everything. There are sometimes not so good ideas which are kind of dangerous. If you are ironing something, you should really don't do anything next to that. And driving, of course, should be solely to driving as well. So on this more everyday side of things, or philosophical side, one could, oh no, this is probably the male dream of multitasking. So, yeah. So one quote I found, I don't know from where it is that the term multitasking has been invented because we needed another word for that we are unable to focus on the task at hand. So, that is actually would be much more better if we could focus, because in everyday life a lot of our multitasking activities need to be. So in our office we could easily turn off the email notification. We don't have to look for every spam mail immediately. We could just go on whatever we are doing for half an hour and then check email every half an hour, for instance. Okay. To bring it back to a more cognitive side of things, let's say a working definition of dual task performance may be performing two or more actions concurrently. So what does concurrently mean exactly? And in this context, I would like to define it to do two things really at the same time, in parallel. So, for instance, using a phone while driving, but not the fast switching between tasks. So not this example we had before, starting an email, then having a phone call, and then continue writing the email. That wouldn't be a dual task performance in this, with this definition. And to illustrate that, you could say we want to have, in this example, this is from computer science, we want to have a task really running in parallel and not a fast switching between.
Yeah.
Okay. And in cognitive psychology and cognitive neuroscience, usually when we talk about working two tasks in parallel, we speak of dual task performance. And when we have the rapid switching between tasks, then we actually would use task switching paradigms to investigate that. So just to make the distinction clear here. And we want to use the dual task paradigm to find out whether people really can truly dual task. Can you do two things in parallel without performance decrements? So the same ongoing performance. Or is that not possible? And if it's not possible, then why is that? Where are the limitations? Okay, so can people truly dual task? Do two things at the same time without some being slower, being more ever pronounced? What do you think?
Yes.
I think it's always sacrificing attention in one task from the other.
I think it depends on whether it's the same category of task. I think, in a sense that like you can walk and chew gum at the same time. You know, there's sort of like different parts of the brain being used. But if like a task competes for the same brain space, I think you could get interference.
So one could say yes and no. Sometimes it may work, sometimes it may not. So examples for usually perfect multitasking. You can walk and talk at the same time, usually. You can sit in the train, watch the landscape and listen to MP3 music or whatever. For professionals, it has been shown that typing and shadowing. So what they have been doing, they were typing something, so from a written text they were copying, and had headphones and were presented words and were just shadowing, speaking out loud.